All right, so lesson 4.07 is about thermochemical equations. So we're going to talk about heat changes in relation to phase changes and chemical reactions, and kind of how to interpret a written out thermochemical equation. All right, you want to make sure that you are able to describe what's going on with the heat in these types of changes and reactions. All right, that might be reading something out of the equation, or it might just be, thinking about what's going on and deciding if heat should increase or decrease. All right, but you'll know you've got this down if you can write your own thermochemical equation based on a scenario and explain what it means. So, up to this point, we've kind of dealt with our chemical equations like this. So, what information can you tell me based on what you see here? All right, pause the video if you need to kind of think about this. But, some things that I would note is that you need 1 C2H4 for every 3 oxygens. You're going to make 2 carbon dioxides and 2 waters. If you really remember stuff from chemistry A well, you might know that, oh, hey, this is a combustion reaction. So I know it's also going to give off energy, not that that's written in the equation. Let's see, what else? That's probably all I can get from just the way this one's written. When we write thermochemical equations, it's going to look something like this. All right, so what's some more things that you can get out of this? Hopefully you are noting that, hey, there's these things. If you don't know what they are yet, that's okay. But venture a guess. What do you think the little g stands for? So, we will eventually find out, but I wouldn't be surprised, especially if you notice that oxygen and carbon dioxide are in here and have those little g's. That might be a big hint there. You should also notice that there's this. All right, so what do you think that delta H is? Considering that we're talking about thermochemical reactions and changes in heat and things like that, I'm betting you probably said something related to heat. And if you remember from our heat capacity equation, delta T means change in temperature, so delta H is change in heat. All right, change in. What do you think it means when that delta H is negative? All right. Again, this one I'm going to leave a little suspenseful here. We'll find out what that means in a little bit. But think about it. See if you can come up with a prediction of what you think that means. Same thing with these little guys. So, before we get back into that chemical equation, I want to take you through some stuff that I think you can logic your way through. So, for example, evaporation. All right, when we take a liquid and turn it into a gas, what happens to the motion of the molecules? All right, so do the molecules move more or less? I hope you were saying more, all right, because we know gases can spread out to take up the entire space surrounding it, so they've got to be able to move around more than a liquid can. All right? So, if there's more motion, what does that mean about your kinetic energy? All right, that means your kinetic energy increased. Kinetic energy is the same thing as thermal energy, in case you didn't remember that from an earlier lesson. All right? So kinetic energy and thermal energy are directly related to each other. So now let's think about the opposite. Or I guess what that should also mean is that means your thermal energy goes up too. All right? What happens when we go the opposite way? We freeze something. We go, say, from liquid to solid. All right? In the solid form, the molecules are going to move, I hope you were saying less, which means your thermal energy goes down. All right, you can also think of it as is lost. All right, if it goes up, it's gained. If it goes down, it's lost. And thermal energy, any change in thermal energy is what? And this is where everything gets tied together, heat, right, or delta H. Right, so any change in thermal energy, we can quantify it as that delta H, which is also, it's your change in heat. So, a little bit of note-taking for you. All right, this first part should make intuitive sense based on what we've talked about before, because we know that sorry, I actually want to change this word to gained. Or you can even think absorbed. All right, so the system, whatever molecule is going through this phase change, heat is absorbed when you go from solid to liquid to gas, right? And that should make sense because we go from not moving much to moving some to moving a lot. And so heat and energy has to go in there to provide that motion, all right? And then the opposite happens when we go from gas to liquid or liquid to solid. Some of that energy is lost and given away, all right? Now, the trick, something that's interesting and something you guys want to make note of, is that during the actual phase change, so during the transition from ice to liquid or liquid to ice, there actually isn't a temperature change. The only thermal energy change is specifically related to the motion of the molecules. All right, so your kinetic energy changes, all right, because the molecule is changing, but your temperature doesn't change. And this is where heat and temperature definitely find their difference. Heat doesn't always have to involve a temperature change, but it always needs to involve a kinetic energy change. All right? So, something to keep in mind as far as your signs, all right, and this is for state changes. If you are going to a point where the molecules are moving more, all right, so melting and evaporating, going from solid to liquid or liquid to gas, that means in the system, the heat has increased, and your heat value will be positive, all right? So the sign goes with what the system's getting. The system is getting more heat. Likewise with state changes, if you're going the other direction, and you move less, so we, condense or freeze, the heat decreases in the system, some of that is given off, and you have a negative delta H, all right? So it's kind of knowing when you have a positive or a negative sign is very important to understand what that means is going on with the heat. The system is gaining the energy and the heat if delta H is positive. The system is losing the energy or the heat if delta H is negative. So if you hadn't already thought of it, that little g, all right, well, so when you're writing thermochemical equations, you actually do need to include the state of the molecule. The reason for that is actually something a little bit beyond this class, but the state of the molecule affects how much energy can be gained or absorbed. So if you start out with, say, a solid reactant versus a liquid reactant or something like that, that can change how much energy is produced or absorbed. All right? So when writing thermochemical equations, you need to make sure to include these. All right? So gas, liquid, solid, probably self-explanatory. You guys know what those are. Does anyone know what aqueous means? So you're watching this. You hopefully are catching that there, that sounds kind of like aqua. That means it's probably got something to do with water. So what aqueous means is it's something that is dissolved in water. All right. A common way to know that something's dissolved in water is if you have a molarity associated with it. All right, so like, 1.0 molar hydrochloric acid, something like that. All right, or you might be told that it's dissolved in water or that it's aqueous. But if you see that, that's what aqueous means. It means that the actual chemical itself isn't there all by itself. It's there in water. But the water isn't part of the reaction. So, let's see how you do with this one. For the following physical reaction, which represents the change in heat? All right? So if you look this carefully, I call this a physical reaction because we're not changing chemicals. This is a state change. This isn't a chemical change. This is a physical change. But this is one reason why you want to make sure that you include your states in there. We are going from solid to liquid. So we are going from less motion to more motion. So our molecules are moving around more. Our molecules should be gaining energy. And if they're gaining energy, delta H should be positive. Another thing tying this back to earlier in the unit, let's see if you can draw this conclusion here. Would we call this exothermic or endothermic? Since the molecules, the system is gaining energy, that means the energy is going into the system, so it's endothermic. All right, so back to our reaction. All right, we know everything in here was a gas. All right, we know that the heat given off, because it's a negative sign, so that negative means that the heat is given off, was 1928 kilojoules per mole. So that means for every mole of this reaction, so every mole of the C2H4 that we put into this and have react, that much energy is going to come out. And can we get a little further? Since we know that the heat is given off, we also kind of know this is a combustion reaction. What would we classify this as? If you're not sure, I'm thinking exo versus endo. Heat's being given off. That negative delta H lets us know it's going to be exothermic. Alright, so another thing here that you can make note of on a piece of paper or something like that is a positive delta H equals endothermic. A negative delta H equals exothermic. Alright, so let's see if we can put this all together and get you to write your own thermochemical equation. So, pause the video, try this on your own, and then turn it back on and see if you got it right. But we are going to react solid calcium and aqueous hydrochloric acid. Remembering my states here, to create aqueous calcium chloride. Formula's given to me, I didn't need to remember that one on my own. And hydrogen gas. All right, so good start. We've got our calciums and our hydrogens. Blast from the past. Is this equation balanced? If you don't remember what balancing means, that means that every atom you put in comes out. So for example, we put 1 calcium in, we get 1 calcium out. Good. In the HCl, there's 1 hydrogen, but we get 2 hydrogens out. Oh. And same thing with chlorine. We put 1 in, but somehow we magically get 2 out. So to fix that, we're going to throw in a coefficient. If I put that big 2 out front, that doubles the hydrochloric acids. So that doubles hydrogen, doubles chlorine, and now we're putting 2 hydrogens in, getting 2 hydrogens out, 2 chlorines in, getting 2 chlorines out. So you are going to have to do something like this in the part 2 of your test. And I bet you there's going to be a balancing part in there. It'll be something kind of simple like this one, but don't forget to do that. All right. This releases 1200 kilojoules per mole of heat. What is the thermochemical reaction? All right, so the only thing we're missing in our reaction here is our delta H. And I know that's going to have something to do with that 1200 kilojoules per mole, and it releases it. So that means we are giving it away. We are losing that heat. So that should be a negative 1200 kilojoules per mole. And my next question to you, is this exo or endothermic? Make sure you can explain why, because that is going to show up. That's on the part 2 of your test. You're going to have to create your equation and then explain what that equation tells you. Alright? So you're going to want to tell me some things like, oh, it's negative change in heat, which means it's exothermic, or it's positive change in heat, which means it's endothermic, something like that. Okay? So, this makes sense? Great. If it doesn't, come see me, get help.